Most economic models operate on the assumption that extreme weather creates a temporary pause. A port shuts down for a storm, the skies clear, and global logistics resume exactly where they left off. The data from the 1997 to 1998 El Niño contradicts this. Following that event, the global economy suffered a $5.7 trillion drag spread over the subsequent 5 years. Economists refer to this as GDP scarring. When a municipality spends a decade rebuilding collapsed coastal housing and eroded infrastructure, that is capital permanently diverted from innovation and growth. Current projections scale this threat up, estimating a cumulative global income loss of $84 trillion by the end of the century due to intensifying cycles. Predicting these massive capital destructions requires looking past descriptive meteorology, tracking rainfall or wind speed, and analyzing the thermodynamic engine driving the Pacific Ocean. For risk analysts, calculating long-term macroeconomic exposure is impossible without first modeling the thermodynamic boundary conditions of the Pacific Basin. This cross-section of the Pacific Ocean basin maps the normal boundary conditions of the water column. The critical metric here is the depth of the thermocline, the boundary between warm surface water and cold deep water. Notice the eastern depth, HE, compared to the western depth, HW, and the horizontal wind stress anomaly, tau. Under baseline conditions, easterly trade winds push surface water west, allowing cold water to well up in the east. This temperature gradient fuels the very trade winds that create it, a mechanism known as the Bjerknes feedback loop. The system's behavior is captured by a simple differential equation, where the eastern depth equals the western depth plus the wind stress anomaly. When wind anomalies occur, they trigger Sverdrup transport, forcing heat to flow north and south away from the equator. This initiates Phase 1. The trade winds and Walker circulation weaken. Without that wind stress, warm water sloshes eastward, pushing the eastern thermocline deeper and triggering an El Niño condition. During Phase 2, Sverdrup transport continuously discharges that equatorial heat toward the poles. Over time, this leaves the entire equatorial basin with an anomalously shallow thermocline. In Phase 3, this shallow thermocline allows cold subsurface water to easily breach the surface in the eastern Pacific. This upwelling of cold water triggers the inverse condition, La Niña. Finally, in Phase 4, the cold eastern waters strengthen the Walker circulation, kicking the trade winds into overdrive. These enhanced winds import heat back into the equatorial basin, resetting the system. El Niño and La Niña are highly predictable, self-sustaining thermodynamic loops governed by delayed oceanic heat transport. The physical architecture of this oscillator is currently mutating, producing a variant known to climatologists as El Niño Modoki. This top-down heat map shows the Pacific Ocean during a classical El Niño. It operates as a binary system, with maximum sea surface warming concentrated tightly along the eastern South American coast, near Peru and Ecuador. The Modoki mutation disrupts this. The warming anomaly relocates to the central Pacific, around the dateline, and is flanked by pools of cooler water in both the far east and the far west. By moving the pool of warm water, the Modoki pattern forces the convective atmospheric activity, the updrafts and storm formations, to shift westward as well. Satellite observational data from the 1990s through the 2010s confirms a marked increase in the frequency of these Central Pacific Modoki events. Because the geometry of the thermodynamic engine is shifting, historical economic models built strictly on classical Eastern Pacific data misprice current risk. To forecast these shifts under the pressure of anthropogenic global warming, climatologists rely on coupled global circulation models, or CGCMs. Across the models, one robust consensus emerges. Rising global temperatures will systematically weaken equatorial trade winds. This diagram maps a paradox that CGCMs encounter when predicting future ENSO intensity. Anthropogenic warming simultaneously introduces two competing thermodynamic parameters, an amplifying force and a damping force. On the amplifying side, as the oceans warm, the boundary line of the thermocline rises closer to the surface. With a shallower thermocline, sea surface temperatures become highly sensitive to even minor fluctuations in depth. On the damping side, the baseline increase in surface temperatures triggers a higher rate of atmospheric heat loss. This constant venting of heat into the atmosphere actively suppresses the formation of temperature anomalies. Because these two variables cancel each other out in unpredictable ways, current models cannot reach a consensus on whether future ENSO events will broadly increase or decrease in amplitude. This high degree of modeling uncertainty means risk analysts must stop relying on universal global forecasts and instead map highly localized, nonlinear downstream shocks. The thermodynamic uncertainty in the Pacific dictates severe biological realities, starting with the collapse of the Peruvian upwelling system. When eastern Pacific waters warm, the habitat for cold water species constricts. This decimates the Peruvian anchoveta, the world's largest monospecific fishery, severely impacting the local export economy. Conversely, the Modoki pattern pushes yellowfin tuna eastward into different exclusive economic zones, drastically increasing their catchability for certain Pacific island nations. Moving west to the Galapagos Islands reveals an even sharper biological bifurcation, driven entirely by localized rainfall shifts. The anomaly creates a massive boom for terrestrial species. Islands that typically experience drought conditions suddenly flood with vegetation, leading to rapid growth and survival rates for animals like the Galapagos giant tortoise. Simultaneously, the warming sea temperatures wipe out the marine food web. Without cold water nutrients, species like the marine iguana can experience up to a 90% population collapse during a severe event. A singular thermodynamic shift creates total ecological divergence. These localized biological collapses serve as a template for understanding how physical anomalies trigger cascading economic disasters. Biological collapses in the Pacific are mirrored by macroeconomic infrastructure collapses across global supply chains. Modoki-altered Walker circulations actively suppress rainfall over critical trade choke points. We see this acutely in the desiccation of the Panama Canal, where severe water shortages recently forced authorities to slash daily transits from 36 vessels to fewer than 20. Ships turned away from the canal must reroute via Cape Horn. This adds 14 days and millions of dollars in fuel costs to a single journey, violently spiking global freight rates. These Modoki-driven droughts simultaneously hit agricultural belts in Southeast Asia, slashing crop yields and compounding global inflation. ENSO is a mathematically definable thermodynamic loop. Mastering the mechanics of the recharge oscillator and the variables of CGCMs is an absolute prerequisite for navigating the $84 trillion shadow looming over the global economy.